about a very interesting DSL that is research group that we're working on. So, welcome Uday. Yeah.
So, thank you, Vivek, for the kind words, and I'm really happy to be here and presenting as part of this forum. And so, I'd like to thank my host for inviting me. So, this talk, as Vivek mentioned, is on a domain-specific language called Polymage that my group has been working on for the past 2 years. And like most groups in high-performance computing, my group works on developing new programming and compiler technologies to improve programmability, performance, and portability. As most of you know, programmability is how easy is it to program a particular architecture. Of course, you want to go faster, so performance, you would like to reduce execution time, maybe reduce power consumption, and portability is the ability to run on all kinds of parallel architecture. And if you really look at all the approaches we have to parallel programming, so I've just classified them this way. So you have, if you want really good performance and you're willing to spend a lot of time, you can go and program in C++ and then use all of these programming models, OpenMP, CUDA, MPI, and so on. And so you get really good performance, but you spend a lot of time, right? And then the next level of abstraction, you use library-based approaches. You write your program in terms of highly optimized libraries, like BLAST libraries, MKL, and so on. So it reduces the effort involved in programming. But again, you lose something because all of these library calls are sort of opaque to the compiler, and your program is sort of locally optimal, but it's not optimized globally. Right? And then obviously you have other higher level languages that provide you abstractions like dynamic typing, garbage collection, and the price you pay for these abstractions is you lose the performance, although it improves programmability. And finally, you have ultra high level languages like R, MATLAB, and so on. And it takes, these are extremely productive, but again, you lose performance. So as you go down, programmability improves, but performance goes down. So ideally, you would like the performance of this class of approaches and the productivity of this class of approaches. So the problem I'm going to address is how do you get both? And so one solution to this problem is the design of domain-specific languages and compilers. So you pick a particular computation domain which has some set of patterns, and you basically exploit a lot of domain information to improve programmability, performance, and portability. And so you identify a domain, you build a new language, and then you build a compiler and optimize the support for it. And so the goal is to get the productivity of ultra high level approaches, but along with the performance of like manual approaches. That's the goal. And so the real advantage we have here is the compiler really has a lot of information about the kind of computations it's trying to optimize. So it can do a better job of optimization. So it knows about dependencies much better, and so on. And so this basically gives you both productivity and performance. However, as most of you know, there's a problem with the DSLs. Well, the big problem is that they are too specialized. And if you're too specialized, you run the risk of becoming extinct. So use Dodo, it's extinct because it was, so some of you may know that it's specialized to the island of Mauritius in the Indian Ocean, and so it had no way to defend itself, and it couldn't adapt, and finally it's extinct. So if you have a DSL that's specialized to a domain, and it can't adapt as you have new computation patterns, you're going to have a few users, and maybe it's not going to succeed. So that's one of the difficulties with DSLs. And obviously, you don't want to learn a new language. You come up with a new language like a DSL, and then you want it to be adopted. People are usually comfortable with whatever language they're programming in, C, C++, Fortran, and so on, maybe Python, and so on. And so you don't want to really learn new syntax. So that's the other disadvantage of DSLs. However, these are not real problems because I'll show that DSLs can be embedded in existing languages. So you don't have to learn a new language. So you can use a host language and you can embed your new domain-specific language into that host language. And the second point about DSLs being specialized, of course you can start with a particular domain and you can go on expanding. So I believe when MATLAB started, it was a language just to do operations on matrices, but now you can do all kinds of scientific computing with MATLAB. So as long as you grow and you get more and more users, it's fine. So you can become more general purpose and you have more users and so on. And one of the big advantages of the DSL compiler is that the DSL compiler knows about all the routines that are being used, and so it can do cross-call optimization. So typically when you write using a library-based approach, the library routines are sort of opaque to the compiler, whereas DSL actually knows about the semantics of these routines and can make global decisions on optimizing for parallelism and locality. So that's one advantage. And you can also have a single source and possibly target multiple architectures, like shared memory, distributed memory, a combination of the two, as well as maybe accelerators like GPU and so on. So that's an advantage that a DSL compiler. And so it's not just the expressiveness argument. I mean, a DSL is highly expressive, and a lot of people who have designed new domain-specific languages have tried to make it very expressive and very powerful, but since we are interested in high performance here, expressiveness is not the main claim or the contribution, but what's important is what the compiler does with the DSL. How does it exploit the domain information to do a good job of optimization and automatic parallelization? So that's the goal. And so how do you go about this? You first select a domain which has well understood computation patterns, and you basically design a language and an optimizer for it. The rest of this talk, I'm going to talk about Polymage, which is our DSL compiler for image processing pipelines. And so these are mainly used in computational photography, embedded vision, image analysis, and enhancement. Okay, so what are image processing pipelines? An image processing pipeline can be represented as a directed acyclic graph of nodes. So you have an input image that goes into the pipeline, and then so each box here applies some kind of a filter on the image. So it takes the image, then you get these two outputs, then you apply another filter and so on, and you get the output image over here. So this is Harris corner detection, which detects all the adjacent corners in this image. And so you start from here and you get this. Okay, so what's inside each of these boxes? So each of these boxes typically has a simple data parallel operator that applies on the entire image. And I'm going to show you some examples. So, for example, each of these boxes could be something like a point-wise operation, where you take the color image and you convert it to grayscale. It could be a stencil operation. So here it's you're computing the image derivative. As you can see all the edges here. So it's a simple stencil operation. It could be a downsample. You take a larger image, create a smaller image. It can be an upsample, the reverse of that. So these are really simple operations. However, you can combine all of these in some complex way to realize a particular image processing pipeline. So this is pyramid blending, where you take these two images, and this is an image processing pipeline that has, let's say, about 20 to 30 stages inside. And it takes these two images, blends these two, and produces this as output. And if you look at this, here in this image, you'll see that the background is in focus. Over here, the foreground is in focus. And in the output, you'll see the background and foreground both are in focus, but the object in the middle is not in focus. So this is something that you can't get from a regular camera. So this is an example of computational photography, things that you can do in software. And many of you would have seen some of these effects in, for example, with your Android smartphones. You have all these features like lens blur, panorama stitching, and so on. So these can be implemented as image processing pipelines. And so this is a complex image processing pipeline, and the image goes in. The up arrows represent upsampling, the down arrows represent downsampling. So what we would like is, so here's the algorithm. So we don't come up with algorithms, but given an algorithm, we are trying to provide a language that can easily express this and then generate high performance code. So given that this is the algorithm of what would be a good DSL and an optimizer that exploits domain information. So if you look at image processing pipelines, again, where are these pipelines used? Okay, on social networks like Facebook, Google+, you would have seen Google+ Auto Enhance. Again, this is an image processing pipeline. So on all camera-enabled devices, you go from a raw camera image to the final processed output. That process itself is an image processing pipeline. So the domains are in particular computational photography, embedded vision, medical imaging, and so on. And so they're used on smartphones, data center scale, workloads, etc. So what is the current challenge with respect to programming image processing pipelines, and what's the state of the art here? So again, if you go back to that example that I showed you, Harris corner detection, where you have, I showed you the DAG. If you write a basic implementation in C, so it takes about 354 milliseconds to run this sequentially. Okay? And then if you try to, as I said, each of the nodes in the DAG is parallel, so you can parallelize each of that. And then if you do parallelize all of that, you will get a speed up of 7x. It runs in 53 milliseconds. However, if you spend a lot of time and tune for locality, parallelism, vectorization, you can almost get a speed up of 29x. So there is a big difference between a straightforward parallelization strategy and NF or another approach which takes a lot of time. So our objective is to go from here to here completely automatically. So this is the sequential performance, and this is easy to get, but this is really hard to get. And so the key is you have a lot of parallelism in image processing pipelines. It's just that it's very difficult to parallelize that effectively, that is, extract both locality and parallelism and get these kinds of speed. Okay, and so we would like the performance level that we obtain with manual tuning and without all the difficulty. And so we do this by actually proposing a DSL that's embedded in Python, and it allows you to express compositions of all those patterns that I showed you, upsampling, downsampling, stencils, and point-wise operations. And the DSL is designed such that the compiler really has a lot of information about the language and is able to do a good job of optimization. And we use lots of complex combinations of well-known transformations that are customized to this domain to actually generate high-performance code. So again, I'm not going to focus on the language. It's the optimizations and the compiler transformations that are more important. But very quickly in this slide, I'm showing you how the language is embedded in Python. So you have this algorithm, Harris corner detection, that takes, this is the DAG. So this is what someone who knows about the algorithm is familiar with. So it's embedded in Python. For every box that you see in the DAG, you have a function in this DSL. So the DSL basically says, here are the functions. So each node in the DAG corresponds to a function. So for example, you have IXY, which just multiplies two images, IX and IY. So you just say IXY defines pointwise IXY. So the language, the description is functional. Okay, and what our compiler does is looks at all this specification and then generates a C code, optimized C code for this, compiles it on the fly and runs it. So we don't execute anything in Python. So it's just the glue code that is in Python. And so this is the DSL specification. And so the compiler looks at all of this. It knows everything about the dependencies. And then there is optimization that I'm going to talk about. But ultimately, it builds a pipeline, does all the transformations, generates the C code, compiles the C code on the fly, and then sort of you have optimized code running. So please feel free to ask questions in case something is not clear. Okay.
So yeah, I'm still confused what you said about taking your DSL and embedding it in Python. Is is your if I wrote a program in your language, is it also well-formed Python, or are you just borrowing from Python syntax?
So it's a very good question. So that's where we would like to know. So this is not a valid Python program. So this is, we're just doing meta programming here. So it's just describing the language in terms of Python. So it's not a, because it's an embedded DSL, and the embedding is what I call deep. So it's no longer, so it's a problem if you want to debug the code, because you no longer have a valid Python program to check. So you just have to go through our DSL and it will generate the code, and you basically have optimized code. This is not a valid, it's just a description of this DAG over here.
Because I'm so confused by what you mean by embedded in then. What does it mean to be embedded in Python if I'm not a well-formed Python program?
Well, it is it's a well-formed Python program. I mean, you run the Python program, and then you will get the code for this. But you're not executing Harris corner detection in Python. So that's what I meant.
Okay.
So it's a well-formed Python program. So sorry, I think that's what it's a well-formed Python program. However, you're not executing the algorithm in Python. So there are other DSLs where you actually have a host language and you embed in that. And so it's also a valid program in, let's say, whatever language is, Scala, right? It's a valid Scala program. And then there's a DSL compiler that's sitting behind the scenes and it's generating C code for that part that you want to optimize. And so you also have an optimized version. So you have basically two. You can always debug and get a working version with the host language itself. And the DSL gives you the high performance optimized.
Okay.
So yeah, so it is a valid Python. At the end, we have something called to build pipeline, which is where our compiler runs and looks at all this information, does transformation, and then generates. Okay, so as you can see, there are no loops here, so it's sort of data handling. The loops are implicit, and we've also abstracted away memory allocation. So at no point do you say that, okay, here's the output image. So you just have an input, and the programmer says, this is what I want. All the intermediate memory allocation has been sort of abstracted away from the program. Okay, so the next part is, how do we take this, sorry, question please.
Are those functions also written in DSL, or are they?
So yes, the function description is here. So let's say you have a stencil, so you can see here, it says apply this stencil on the entire image. So the compiler has full information about what's going on inside these boxes, right from this code. But we will generate C code for this. It's right now it's just expressed described in Python, but ultimately you generate loops and.
So is that just a call to a function stencil that the compiler already knows, or is that the full definition?
Oh, this is the full definition. So it's basically applying this 9-point stencil to the entire image. So that's all there is. So the compiler knows everything about what's inside this box as well as the dependencies between. And at the pixel, at the point, it knows it has point-wise dependencies, not coarse dependencies between these boxes. Okay, so let's look at the optimization for this. And imagine that you have these different boxes that I showed you in the tag on the vertical axis, and then you have the image dimensions on the x-axis. I'm not showing the third dimension, so the image is two-dimensional. So I'm just showing one dimension, but imagine that there are basically two dimensions, and I have these functions on the y-axis. And so this is the image. Imagine that this is the image processing pipeline. You have f in, and then f1 uses f in, f2 uses f1, and f out is what you finally want. It's the output. Okay, so if you represent all your computation as these small circles, right, so you get this, and then if you represent, if the arrows are the dependencies, so you can see f2 of x depends on f1 x minus 1 and f1 x plus 1. So that's what this specification says. So this is what you want to execute, and these are the dependencies. And so what's a good way of parallelizing this? So this corresponds to one node of your DAG. So here the DAG is just 3 nodes, one after the other. And as you can see, there are no horizontal arrows. So a straightforward way of parallelizing this is as follows. You just parallelize. So this is the dimension along the the image extent. So you can divide this work across cores. You parallelize, then you have to synchronize, then you parallelize, barrier, parallelize. So basically you have two synchronizations, and so you have a good parallelism. So the image is big enough, right? And so you get enough parallelism, and so this is a very straightforward way of parallelizing, and this is the first thing you will do using OpenMP and so on. However, there's a problem. Usually this image, well, this doesn't fit in your cache, right? So as you can see, you have parallelism along this dimension, and there's also the other dimension that I'm not showing you. It's a two-dimensional image. The locality is in this direction, right? So you see all these edges in this direction. So this way, you get good parallelism, but you get very bad single-thread performance because, let's say, one core executes all of this, and then it goes here, and you'll again have cache misses because this will no longer be in cache, right? So this is straightforward, those who have studied loop transformations. So you get good parallelism, but you get poor single-thread performance, and if you try to run it on several cores, you will be memory bandwidth bound. Ultimately, you won't see much speed up. Okay, so how do we fix this? So there are well-known tiling strategies where you actually take a small piece of this data set, and then you construct these parallelogram-shaped tiles. Here, square tiles would be invalid because there shouldn't be any cycles between tiles for a tiling to be valid. And so you can execute one tile after the other. So this fits in cache. Assume that this is small enough to fit in cache with the tile size. And then you execute all of this. And then one process executes this tile, another process executes this tile, and so on. So in this case, you have good single thread performance, but there's an obvious problem here. You lose all parallelism because this tile would need values from this boundary here. And on the y-axis, as I said, you have all this different image processing, the nodes from the DAG, so you have a fixed number of nodes. Right? And so you essentially end up losing all parallelism here because this tile depends on this depends on this, and so on. So you have good single thread performance, but no parallelism. Okay, so how do you fix this? How do you get both parallelism and locality? Another well-known technique is called overlap tiling. What this does is tries to break the dependence between adjacent tiles by doing redundant computation at the boundaries. So people have used this technique both sort of when parallelizing manually, as well as there are some compiler techniques that do this. So they've done this for stencils. So the idea is to use overlapping trapezoids. So you look at this, and then you see that to compute this, I need everything that's in this trapezoid. So to compute this, I need to take this and compute this based on this and so on. And so by doing redundant computation at the boundaries, so you can see that this is computed redundantly by this tile as well as this tile. So by doing this redundant computation, you break the dependence between adjacent tiles, and so all these trapezoids can now be executed in parallel. Right? So this way, you get both parallelism and locality because you can adjust the width of the trapezoid based on what you can fit in cache. So in reality, this is a square pyramid because you have a two-dimensional image. I'm showing this as a trapezoid, but so you have this kind of square pyramid where the base of the pyramid fits in cache, and then you compute based on that. Okay, so this way you get parallelism, locality, and another good thing is you can put this in a local buffer that's contiguous. As you can, this is not matrix multiplication, as in because you have a limited amount of reuse, right? The amount you have reuse here and here. So it's a fixed amount of reuse, and it's absolutely important to have sort of local scratch pads. And so this technique goes well with storage optimization as well, because you can keep this in your local buffer, and then once you have this in buffer, you can just compute all the way. You never need any data from another type. Whereas if you look at this approach, and even some other approaches like diamond tiling and split tiling, you have a dependence between this tile and this tile. And if you want to put this in local buffer, you need to find a way to get this data and somehow index this and use it over here. Whereas overlap tiling is really good for even sort of local buffering. However, the downside is you do some amount of redundant computation, and this might be a good fraction of your entire tile size. So you want to reduce the amount of redundant computation. Any questions? Okay, so this was a very simple image processing pipeline. As you could see, all these arrows look the same between F1 and F2 and F2 and F out, but real image processing pipelines are more complex. So as I showed, you could have a downsample, you reduce the size of the image, and so on. And so the dependencies might look more complex. For example, the dependence distances can change. So you have an image that is of, let's say, n cross n. You downsample and you create image of size n by 2 cross n by 2. And as you can see, the dependence distances vary, and they are a function of this along the x-axis. So here you have it goes a distance 1, 2, over here it's 3, and so on. And here, this dependence goes a distance of n by 2 along this direction. So when you have such non-uniform dependencies, it's not easy to construct overlap types. But you can use, again, well-known transformations like loop scaling, for example. You take this function and scale this by a factor of 2. You take this and scale this by a factor of 4. And all of a sudden, you have this. So if you just do this relative scaling, now you see that all the dependencies become sort of constant. Yes.
So these transformations are like linear transformations.
Yes.
What happens if they're quadratic or cubic?
Oh, we are only looking at linear or affine transformations because code generation under these transformations has been well studied. I mean, so most literature in this area has sort of gone as far as, let's say, affine transformations. Because ultimately, I mean, if you just transform it and you're not able to generate code, then it's of no use, right? So, yeah. In fact, the transformations that we consider are a strict subset of affine transformations, so linear plus a constant. So if you apply this scaling, now you see that all the dependencies have become short, right? So this is like 1, 1, this is a 2, 1, and 1, 2. So they're all uniform, they're all nice and uniform, and now you can construct overlap types from this. So if you look at these 3 points, and if you just try to construct, so now I'm going to talk about a more precise way to construct overlap types. So the existing techniques in the literature that were general purpose and that would look at dependencies and construct overlap types would end up with a shape like this. And as you can see, if you use a shape like this, you would just have too much redundant computation. That if you look at one trapezoid and go to the next trapezoid, they have a large overlapping region. So if you just try to look at these 3 points, and then try to look at your dependencies. As I said, a tile is atomic. There shouldn't be a cycle between tiles. So you should not have a phase where there are dependencies both coming in and going out. So if you look at this tile, everything is exiting the tile. There's nothing that's entering the tile. Okay, you look at any of these spaces, the things that are going out, but there's nothing that's coming in. And the way existing techniques would come up with this tile shape is by looking at the most constraining dependence. So if you look at dependencies as distance vectors, right, those who have done a compiler course would know that. So if you, how would you determine this slope? The dependence that goes the maximum distance along the negative x-axis is this one. It's between F2 and these 2 stages. So it's 1 in this direction and -2 in this direction. And so this is the dependence that would determine this slope. Okay. And now you look at all dependencies that go in this direction, and you try to look at the most constraining dependence. In this case, it would just be 1, 1. And so that determines this slope. Okay. And we use these dependencies to determine your left slope and right slope, and this is a valid type. But as I said, if you follow this approach, you'll end up with a tile shape that's too conservative. You can do something much better, which is this. If you really look at this point, and if you go backwards and see what part you needed to execute to compute this, you'll find that I think I'm going to connect my charger. Is there another flux point here?
Yeah, structures.
Down. Okay. Okay, so you can do something better. You look at this, and then you try to precisely look at the dependence between individual stages, something a general purpose approach doesn't do. But this is the point behind building a DXL compiler. So these choices do matter, and you can sort of compute a much tighter tile shape. I'm not going to go into the details, but so here's a much tighter tile shape. You could have just done away with all of this. And if you look at these 2 points, you actually just needed to compute only this part. But we would like the shape to be polyhedral so that it's easy to generate code. That is, you want the boundaries to be hyperplanes or sort of linear, right? So that's why we choose this particular shape, and you save this much redundant computation if you are sort of domain specific here. That is, you are aware of all these dependencies between individual stages, and you are not just constrained by the most, the dependence which has the least slope. So ultimately, you have you construct these overlap tiles, and then each trapezoid is executed by one core. Right? Each trapezoid is executed by a thread, and so you have parallelism across these trapezoids. And within a trapezoid, you would get vectorized. You would get vector parallelism, and you have locality. And as you can see, if you reduce the height of this trapezoid, the amount of overlap between 2 trapezoids, it reduces, right? So if you have 1, 2, 3, you have 5 functions on the y-axis. If you increase the number of functions on the y-axis, you would have more overlap. If you reduce the number of functions on the y-axis, you will have less overlap. That is, less redundant computation. But ideally, you would like as many functions as possible on this y-axis so that you can get a lot of reuse. And you start with a small piece, and then you go this way, so you get good locality and you get parallelism. But if you have too many functions, you end up with a lot of redundant computation. So you don't want to do that. Okay, so there is a trade-off between fusion and the amount of redundant computation. So these are the kind of trade-offs a general purpose approach would sort of fail to explore. But these are again very important to exploit. And so as you can see, if you fuse less, the amount of redundant computation reduces as a fraction of the tile size. And ultimately, so this is the scheme. So you would have all of these being executed by different cores. All of this fits in a local buffer that is less than your typical, let's say, L2 cache size. And then you compute based on this. Okay, so if you have an image processing pipeline like this, so I haven't yet talked about fusion. That is, how would you decide which functions to put on the y-axis? So we are not doing any DAG parallelization here. Again, the parallelism that we are exploiting is pure data parallelism. So we are taking these different image processing functions from the DAG and then fusing all of them together. And then we are doing overlap tiling of this. So it's just data parallelism that we are exploiting. And you will take an image processing pipeline like this. So the first step, you would like to group this into some, you would like to group several of these stages and then put all of these stages on the y-axis and then try to do overlap tiling. So a key part of the problem is to determine which stages to fuse together. Okay? And each fused group, right, is tiled using overlap tiling and is parallel. And one group is executed after another. Okay, so we do have a grouping criteria that tries to fuse as much as possible because we want to exploit locality, but I'm just going to quickly summarize this. It will stop fusion when you fuse something and you find that you can no longer tile because the dependencies go in both directions somehow. If you fuse something and you can no longer tile, you will stop fusion. You will also stop fusion when you fuse something and you find that you have to do too much redundant computation to actually get the tiling to work. So if one of these two happens, you will stop fusion. Otherwise, you will just fuse. So in this case, for Harris corner detection, we end up fusing this entire thing into one. So we'll end up putting all of these on that vertical axis. So basically, we're fusing all the stages to yes, sorry, question.
So in the Poshmark stencil compiler, they have a notion of folding their trapezoids in half to kind of do it in 2 stages.
Sure.
To reduce the redundant computation.
Sure.
Is there an analog for that with the heterogeneous?
So that's also called split tiling. Yeah, you have upward pointing trapezoids and then downward pointing trapezoids. So you could use that strategy. Actually, that's one of the strategies that you could use here. I didn't talk about it. So the thing that's complicated about that strategy is, well, you don't have redundant computation, so you do get parallelism and you get locality. But the problem with the strategy is very hard to do local buffering because the downward pointing tiles depend on the upward pointing tiles. So once you execute the upward pointing tiles, and so if you were to do local buffering, it's just going to be extremely complex because the upward pointing tiles will execute and then you need values from this slope, and so you will have to get these values and somehow find a way to index them into the local buffers of the downward pointing ones. So it's just, I would say, extremely complex to implement with local buffering. But what Poshmark does is, I mean, it's all just shared memory. There's no local buffering, so it just works, right? So thanks. So it's, yeah, so that strategy would be really good, but again, without local buffering, a lot of the improvement that I'm going to show will be lost. And so this is one advantage of this overlap tiling, is that completely breaks the dependencies between tiles and makes it easy to do.
So you could do the local buffering with like one round of communication exchange, right? Because essentially it's like saying what I want is...
Exactly, there's only one round of communication exchange, that's fine. But the data that you get, right, the data that's communicated has to be somehow put into the right place of the local buffer of the receiver so that it can do the computation. So that part, the indexing part, is just hard to automate. I mean, you could imagine doing that manually. Again, it's probably difficult, possible, but yeah, trying to automate that is extremely difficult. But yes, you'll only have one round of communication. Sure. Okay, so for a complex image processing pipeline like this one, this is the grouping that we finally come up with. Okay, so you have the red box shows that we grouped all these stages together, put them on the vertical axis, and then did overlap tiling for that particular stage. And so as you saw, I mean, most of the approach is completely model driven, but we do have some auto tuning because we can't model everything. In particular, for the tile sizes, we have basically for the tile sizes we do some auto tuning. So it's good that we know the image sizes. Typical image sizes are 2,000, 4,000, and so on. And so we try a fixed number of tile sizes starting from 32 all the way to 2048. There's also thresholds with respect to how much redundant computation we think is acceptable. So we have these thresholds of 10%, 20, 30%. If the amount of redundant computation exceeds 30% of the tile volume, we stop fusing. We won't fuse anything more because the amount of redundant computation. So these are again based on empirical feedback from empirical auto tuning. So there's just a space of 150 points that we tune on. We will try all of these tile sizes because we have 2 dimensions for the image. So a bunch of 7 tile sizes along each dimension and 3 thresholds for overlap tiling. And each of this 150 or 148 points corresponds to a different fusion structure and a parallelization. And so we will just auto tune over this space and find the one that performs the best. Okay. So yeah, so let's we'll just move on to experimental evaluation. So we we wrote these 7 image processing benchmarks using Polymage, and this column shows the number of stages, the number of nodes in the DAG that corresponds to this algorithm. And so you have 4 stages, 7 stages, 11, and so on. This is the most complex image processing pipeline of 99 stages. So and this is the number of lines of code in Polymage. So the same thing, if you would write in C, it would be several hundred lines of code, C or C++. And these are the image sizes. Okay, so I'm going to do a quick video demo here. So we implemented all of this, and so whatever I mentioned about images can be also applied to videos, where you take each frame of the video and then you apply the image processing pipeline and then you write the output. So you just take each frame, apply image processing algorithm, and then you can time how much, well, you can time the algorithm. So this is just a basic video that's playing. And so this is the first thing that I showed you, Harris corner detection. So this detects all the corners in the image. So this is the original one. And so this is written using OpenCV. So OpenCV is a library for vision image processing. So it has a routine for Harris corner detection, and here you can see it takes about 80 milliseconds to process each frame. Okay, so you can do maybe 15 frames in a second. So this is a library-based approach. And so this is Polymage. This is with the overlap tiling, and the fusion takes 30 milliseconds per frame. Okay, so you can do maybe about 30 frames a second. And this is without the optimization. Okay, so you get almost, so even this is running on 2 cores of my laptop, and the optimized version is also running on the 2 cores of my laptop. But just because you optimized for both locality and parallelism, you see this speed up. So this is with the overlap tiling and fusion, and this is without. It's almost zero. Okay, now this was a simple image processing pipeline. Something more complex, unsharp mask. So you can see the image is this is the original image. This is the sharpened version. So this is a Polymage naive. That is, so by naive I mean the first thing that I showed you. You run in parallel and then barrier, parallel, barrier, and so on. So it's a straightforward parallelization without doing any overlap tiling. And this is optimized. So again, this is also running in parallel, but with the overlapping trapezoids, and it does, all of these benchmarks are memory bandwidth bound, so you really get a lot of speed up if you optimize for both parallelism and locality. And so it takes, it's almost 3x speed up that you get just because you optimize for both. This is the original image. So now something more complex. This is bilateral grid, which does edge-aware smoothing of the video. So you can see the video has been completely smooth. This is the original. But this is a more complex image processing pipeline, and here 100 milliseconds per frame with the optimized Polymage. This is without, you don't see much difference here, but all of this code was tuned for a 16-core Sandy Bridge. I'm going to show results for that later. So on my laptop, you don't see much speed up with optimization here, but in general. And now something even more complex. So this is called local Laplacian filters. As you can see now, it's taking much more time per frame. It does make sense to run these things faster, so that you get, oh, it's almost stuck. I need to kill Thunderbird. Okay, it's much faster. So this is with optimization, and this is without optimization. It tries to improve the local contrast of the image, and this is the pipeline that I showed you, which had 99 stages, and it's the most complicated one. Okay, this was the original. Getting back to the slides. Okay, so This picture summarizes the improvement that you get when you use over the basic straightforward parallelization, the first thing that I showed you. You just parallelize each filter one after the other, and on average you get a speed up of 2.5 to 3 over a straightforward parallelization. So with the overlap tiling, the trapezoids and the fusion, you get a speed up of over 3x. Again, the baseline is also running on 16 cores here. This is on a 16 core dual socket Sandy Wave server. So the baseline is also running on 16 cores. The optimized version is also running. Okay, so the state of the art in this area is a DSL called Halide, and in fact, our DSL was inspired by Halide. Halide is embedded in C++, ours is embedded in Python, but really the language is almost the same. I mean, the computation patterns that are supported are the same, so equally expressive. But in Halide, there are two parts where the programmer specifies the computation, and he also says how to optimize it. Also provides a schedule. So we have basically completely automated that part. So the programmer just needs to say, this is what I want to execute, and the compiler will go ahead and automatically parallelize and do the work. Whereas in Halide, it takes significant effort to come up with a good schedule for parallelization. And so we compared with the manually tuned schedules that were available in the Halide repository, and we actually see that in many cases, the schedules that our compiler generates automatically, they are even better than the manually tuned Halide schedules. On average, you see an improvement of about 1.5 over Halide schedules. And okay, here there's a lot of information, but this is just to say, okay, why are we getting improvement here? So you could maybe just focus on the 16-core case here. So for Polymage, we looked at the optimized code and also disabled vectorization to see what the vectorization efficiency was. So if you focus on the 16-core case, you can see that the difference between the dark red and the light red one here, right? So on the overlap tiled and the fused version, we see that you get a speed up of 3 just because of vectorization, whereas the speed up due to vectorization on the unoptimized version was just, so from 10.3 you go to 16.2. So the baseline is the single core version. Okay? So if you do straightforward parallelization and you vectorize, you get a speed up of only 1.5. However, if you optimize for locality as well and then vectorize, you get a speed up of 3. So it just says that unless your data is coming from the cache, right, you won't see benefits of vectorization. So it's important to optimize for locality for these image processing pipelines in order to get benefits of vectorization. Otherwise, you will see that the code is vectorized, but you don't see a speed up. Similarly, you will see that the benefits, the scaling also improves much more for the locality optimized version, but not for the one that is straightforward, that is parallelized in a straightforward way, just because the latter is memory bandwidth locked. So if you optimize for locality, you get much better, you see much better parallel speed up, as well as you see that the vectorization is more effective when you're running on 16 cores. Any questions? Yes.
So is the difference here due to the locality or something else?
Okay.
Because it makes sense that if you're accessing data more locally, you have less memory interference between the cores, so
Okay.
you're not consuming as much memory bandwidth. But could it be also because of the reddish allocation that introduce more spews and restores?
Okay, so there are many things here. So the interference is less of an issue, but so it's basically simple. If you want to keep the vector pipeline full, right, you need a really high bandwidth. And you just don't have, if you just calculate it, you just don't have the memory bandwidth to keep the vector pipeline full if the data is coming from the memory. If the data is already in the cache, then that's better. So you don't see as much improvement in vectorization effort. Now, with respect to register spilling, and well, that's an orthogonal issue, but I think, I guess that issue would apply to both. a version that's not optimized for locality as well as one that's optimized for locality. But here the difference is because your data is mostly coming from the cache, so the vectorization is much more effective. You're keeping the vector pipelines going. So and you don't consume as much bandwidth when you're running on 16 cores, right? So you see much better scaling because again, your data is coming from the cache. Okay, so we also compared, so Halide, there were manually tuned schedules available, and there were also, there's also an auto-tuning approach that's used with Halide, it's called OpenTuner, and we also compared with OpenTuner. So OpenTuner is not model-driven, it just blindly searches the entire space of schedules, and so our auto-tuner is sort of completely model-driven. And so we tuned it for a day, and again, we get very good improvement from OpenTuner because OpenTuner schedules are really not that effective. That's what we found after 1 day of auto tuning. And we also compared, we also took our schedules and expressed them with Halide because Halide targets LLVM IR, whereas we just generate C code for that DSL, and then we compile it with a C compiler. Basically, we use Intel C compiler. So we are comparing two different systems here. So just to make sure how much of the difference between Halide and Polymage was due to more effective schedules as opposed to the backend that was being used, we took our schedules and expressed them in Halide and then tried to see whether it improves performance over. And so it was possible for these three benchmarks, we could express our schedule in Halide scheduling language, and we already saw this much improvement. And this is because the fusion, the grouping that we came up with was different from the one that was used in Halide's manually tuned schedules. So again, it's not possible to explore all possible groupings, so it does make sense to have a model-driven approach to find the right fusion. And so it's just that our code generator was able to find a better fusion than what was used in the Halide schedule. And so we were able to still get speed up over Halide when we expressed our schedules. And finally, we also compared with OpenCV. OpenCV just runs on one core. They have GPU optimized routines, but they don't have CPU parallelized versions. And so this is the comparison with library-based approaches. So one problem with library-based approaches is you have an API, and if you don't have the routine that you want, you are stuck. You have to write it yourself. You write in terms of whatever is available. So, whereas in our case, you have these patterns that are supported, and we will generate optimized code for any composition of those patterns. So we get a lot of improvement over code that's written in OpenCV. And finally, so these are the speedups that we get, about 2.5x over naively parallelized code with geometric mean, 5x over Halide OpenTune schedules, and 1.7x over Halide manually tuned schedules. And for something as complex as camera pipeline, so our input was just 86 lines of Polymage, and we generate the optimized code that we generate is 732 lines. And this is only 10% slower than an expert-tuned version, which is FCAM. FCAM is an open source expert-tuned, hand-tuned code for camera pipeline. And so you have both productivity and performance. And so finally, where are we going with this? As I said, I mean, a DSL, it's not going to be adopted if it only supports, it's restricted to some set of computation patterns. You always want to expand and support new domains so that you have more users and that it grows. And so we did a lot of other work with time-iterated stencils that we would like to bring it, sort of make Polymage an umbrella DSL for several domains. And we would like to include other domains where these kind of transformations help, in particular time-iterated stencils. Those who are familiar with geometric multi-grid algorithms, they're used in solution of partial differential equations. So there's a direct correlation between image processing pipelines and multi-grid. So even in multi-grid, so like the restrict operator is similar to downsampling, and error interpolation is like upsampling. So we would like to include these domains also, lattice Boltzmann method, more complex image processing pipelines, and deep neural networks and CNNs are emerging domain. Again, there's a lot of similarity between image processing pipelines and this. So the stencil that I showed you is basically a convolution of the image. And so in a convolutional neural network, you have several layers. Typically you have convolutions, and then you have some max spoolings, which is like a downsampling. And so you could potentially apply some of these techniques to this domain. And so you could maybe add these things to the language. And finally, other routines like dense linear algebra, sequence of dense linear, they also fit well with this, and you could reuse a lot of this. And we did a lot of other work with distributed memory parallelization. At the moment, we only target shared memory multicores. But yeah, we would like to bring all of that work into this DSL. And one of the good things here is that we completely abstract the language, abstracts away memory allocation. So the programmer doesn't have to worry about memory allocation, allocating intermediary outputs and so on. And so it gives the compiler a lot of freedom to do layout optimization and do this local buffering, because all you care about is the live out. Whereas if you start from a C code, you're always stuck. The compiler is scared to do these transformations because you don't know who else is using this data, and you need escape analysis and all kinds of things. Whereas a DSL sort of makes this easy. You can just specify input, output, and the compiler can choose whatever layout it wants in between and create local buffers, and you can also, so you get, the memory utilization is low. So we'd like to include all of those things within this optimization framework. And so finally, I feel DSL compilation is the way to go for several domains. And it's not that you don't have to reinvent the wheel. So all the transformations that I showed are some combinations of well-known transformations that were known to the compiler community. And it's just that these had to be tailored to a particular domain, and you get dramatic speedups if you do that. And frameworks like the polyhedral framework that were used for affine loopness, it can be again customized and used in these DSL compilers to do automatic parallelization that's much more effective than what it is with just C. So this was a joint work with two of my master's students, Ravi Teja and Uday. So I'd like to acknowledge that, and I'd like to acknowledge Intel Labs for some hardware and software donation, and Google for a research award, and of course the Halide team for developing Halide as an open source project. So it really helped us. So you can find more details at this URL and in our ASCLOS paper on Polyhedral. Okay, so thank you for your attention.
Is there a comparison between poly image and then standard polyhedral optimizer, such as, say, passing these image processing pipelines to Pluto or Pluto Plus?
Okay.
How would be the performance difference?
So unfortunately, whatever Pluto does is not very useful for these domains because, well, Pluto is good with time iterated stencils, but here you don't have a time loop on the vertical axis. It's just that you have different image processing stages. So what Pluto would end up doing is parallelizing each of these stages separately, either that, or it will fuse all of these stages together. But the moment you fuse, because of the dependencies, you will lose all parallelism, because Pluto doesn't implement overlap tiling. Overlap tiling is hard to implement for shared memory because you have these overlapping regions, and here you'll have, it's not a valid tiling scheme. It's only valid because you use local buffers for these trapezoids. So because Pluto doesn't implement overlap tiling and local buffering, it's pretty much useless for these image processing pipelines. The best you can do is just, parallelize each stage one after the other. So all the general purpose, well, all the polyhedral stuff that had been developed was not useful for this domain because it was special in the sense you had a fixed number of functions. You didn't have the kind of reuse you have with time iterated stencils. And it was absolutely important to also model this trade-off between tile sizes and fusion that we had never explored with traditional loop optimization. Here you see that, I forgot mentioning. So if you increase the width of the trapezoid, the fraction of overlap, right, at the boundaries, it reduces. It's a smaller fraction of the whole tile volume. So if you increase your tile size, it basically means you can fuse more because you can tolerate more recurrent computations. So this was a trade-off that we never explored while doing. We would typically try to fuse, and then we would set tile sizes based on what fits in the cache. But here you fuse, and then you see, oh, you need this much recurrent computation. So it's okay with a large tile size, but it's not okay with a very small tile size. So you have to go back and forth, and it does help to do this auto-tuning and check what fraction. This is, it's very hard to do on starting from C code. Unless you really have this information about the domain, it's hard to do. And these kind of optimizations really made a big difference, like 2x, 3x.
Do you think this kind of technique is directly applicable for making it on GPUs? For example, image processing pipeline
Yes.
is now going on GPUs.
Yes, absolutely. So in fact, Halide also has a backend for GPUs. Yes, so this thing fits very well for GPUs because the terminal that I showed you, you can have the local buffer in the shared memory of a GPU, and there is a lot of parallelism. And some of these pipelines, like bilateral grid, they take a lot of time on CPUs. So yes, I mean you can use. It's just that the parallelization strategy has to be slightly different.
So do you have some numbers, like how much speed up you get? Like
No, we don't have a backend for GPUs yet. But the Halide project has shown very good improvement while running on GPUs, much better than the speed ups they get on the CPU. Could refer to that.
Okay, well, maybe let's thank Uday again. Thank you. Uday is visiting for some time tomorrow as well, so if you'd like to meet with him, Prashant is coordinating a schedule, just let Prashant know.